So this is going to be an unpacking of some of the junk which is rolling around in my head for the past few months while we try and do other things in the hardware space. I still have to track what's happening like in the PML space, and this is trying to unpack where the big tech companies are kind of maybe now going forward to the end of the year. And the problem is like when you see something, that's not where the tech companies are. By the time you see it, they've been doing that for 5 years. So I'm trying to think like where they are, where we would be like 5 years from now. And so it's trying to kind of look at what's coming up, trying to give you some hints about why people might be thinking about certain things. And yeah, it's a wander through my brain. Really. So there's two parts to it as well. There's the easy side and there's the content. So it's like, pick your fighter. Okay, where are we currently? When we think of networks, like traditionally we've been in a sort of unimodal mode, which are very specialized networks which just do one thing: vision, audio, language. Multimodal has been around for a while. There's different ways of doing multimodal. You're just taking two specialized networks or more and you're just blending them together and you're making some kind of joint representation. So this would be like a mixture of experts. GPT-4 is a mixture of experts, at least according to Twitter. It's made up of 16 230 billion parameter models. That's not what people thought it is. This is a very successful approach, and it's an approach which is being pushed forwards. But the fact that they had to make a mixture of experts model for GPT-4 kind of suggests they're kind of running out of runway with good ideas for things that they could make. Now, at the moment, the current excitement du jour is to add tools to these things. So tool use is like a really important direction, and so really we're building knowledge-based AI automation. That's taking us into the world of agents, right? The more you kind of expand the capabilities of these things, the closer you're getting to making agents. The thing that's missing kind of at the moment is a bit of executive planning, because GPTs at the moment aren't very good at that. But if you kind of break down what you need in a cognitive system, and these are cognitive architectures, the planning part, perception part, the knowledge, representations, task execution, we kind of have ideas about these. And people are kind of making a run of this, but the big issue is we still really don't know how to connect this stuff up. So we have lots of kind of disparate ideas about how these things go together, but connecting it up, like, yeah, who knows? Like, we really don't have good models for that at the moment. And so the things that we're making are kind of a bit chimeric. You know, they're these weird kind of monsters with like too many legs, and like we're really struggling a bit to put them together. But if you look at any one of those things, we've got more than 2 decades worth of research of how to make superhuman capable systems which address any one of those problems, right? It's like we are tantalizingly close to being able to do this, but like how we glue it all together is still kind of open for question. If we look at the beating heart of what we're making at the moment, you know, everything's being driven from language models, and you know, I would say we're using these things all along. This is not the way to do it. But these things are very interesting, but for reasons which are totally different than the way that people think about it at the moment. Specifically, you know, we're using transformers, and you know, we have well-known problems with transformers, which are mainly hallucinations. And yeah, let's kind of get into that a bit. So language is a graph. This is not a particularly exciting graph, it's a straight line. But if we extend it a bit, then we find that, you know, it then has to kind of attend to cat and mat. The cat sat on the mat, it was cold. What does the it refer to? Does it refer to the cat? Does it refer to the mat? You start building up graphs of language. And then when you train these models, you just do a causal representation. You just get everything in front of the point where you're going to guess and give it context, which is everything that came before. And you know, that's your training. It's literally just guess the next token on what's come before. We do that over segments of like the equivalent of 10 million books, but totally randomly. You know, it's 10 million random segments of stuff which have no coherence together. It's a lot of information. Like, who's read 10 million books? Interesting note takers. Okay. So what you end up with is this massive, loosely associated pile of graphs with weak probabilistic associations between them. So you end up, now some of those graphs are very powerful. You know, when you've gone through 10 million books and you've got statistical associations from 10 million books, you're going to learn some nuanced stuff. right? Some stuff which nobody has ever thought of. But unfortunately, it's all tied together with like such weak associations that there's no tractable way of using that. So we end up with this big pile of stuff. And what do we do to it next? We train it to follow instructions and tasks. So this is the next training task for typical GPT, is instruction tuning. This is just going to winnow away some of the less probable graphs in there and just kind of leave you with a more usable core. And then we train it with human feedback. And this is to make the thing more acceptable, right? But this is also very destructive. It gets rid of a lot more of the stuff, but in a way which is measurably destructive to the output of the systems. But if you don't have that, then you don't have something which you can use realistically in the commercial space. So after all of that, you still have this big pile of unrelated graph-based material. So that's how it's trained. That's what you're using it. When you come to actually making a query with it, we're doing something slightly different. So a question is a partially observed graph. Why is it partially observed? Because you don't articulate everything that you want to say about the question which you're asking. There's lots of stuff which you keep in your head. There's unspoken stuff which you are thinking about, which is related to the question which you're asking, and those nodes, basically don't get there. The bit which the computer gets to see is the dark bits, which are the bits which are observable. So it has to take that, and based on that, it has to start working through its graphs, and it adds a node, and then it kind of adds another bit of a graph, and another bit of a graph, and another bit of a graph, and hey, it begins to guess, just because it's had exposure to this kind of question before, some of the hidden nodes from the stuff that you've already have in your head about like what the question is that you're asking. So it can sometimes seem kind of magical, and it kind of really seems to get you, but it's just like filling in this extra space from the millions of examples it's had before. Anyway, it keeps going, and with every word it comes samples new bits of graph, new bits of graph, new bits of graph. And this is just going to keep extrapolating. So if you start with a question, meaning of life, it's just going to go until it gets to some logical conclusion. But what if you could put in like a waypoint for it? So something where it's extrapolating into this vast wilderness of solution space can actually control where it goes, as opposed to falling left, it falls slightly to the right. So instead of landing at cats, it lands at a much more reasonable answer. So this is like Bumblebee kind of flying through this solution space, this of jumbled graphs, right? It's just taking a totally random trip, and it can really end up getting bounced around anywhere just by loose probabilities of associations between graphs. What you need is GPS, right? You need to give it some waypoints which allow it to navigate through what it's doing. And this is what you're doing with all of the prompt engineering techniques. So this is kind of the limit of what you can do, but it's fundamentally the basis of it is based on a weak system. It's based on the way it's trained is just, it doesn't give it anything tractable to get hold of. So let's dig deeper. So the first question is where do language models keep their data? So there's a really great paper out, which is the Roan technique, which is locating and editing factual associations in GPT. And so they use a causal flow to look at what's happening inside of GPT, and then they test that over queries, and they can basically map out where things are happening inside the model. And what we see is something kind of quite interesting, which is if you take a sentence like Shaquille O'Neal plays the sport of, and is going to come up with the answer soccer, Shaquille O'Neal, that gets kind of most represented here, which is kind of in the middle layers of the network. And you get this other strong representation at the end of the transformer. So more specifically, if you unwrap the transformer, what you see, and in this image we have like the individual states as they go through. The red areas are attention heads, the green areas are the memory, so this is dense memory, or multi-layer perceptrons. And you see that when it gets to the subject, cat, the cat is stored somewhere in these dense layers. And when it's making, in fact, it's specifically stored in these memory areas of these dense layers. Okay? The dense layers of the midsection of the network. And the structure to build the solution is here in the attention heads at the end of the network. right? So this is this separation between where information is stored and where the structure is stored. And what they showed is that you can go in and you can edit this. So if you want to change, the example they have is they want to change Shaquille O'Neal to Megan Rapinoe. You can do that successfully, which is a surgical kind of change within the network. So yeah, keep that in mind. But these are frozen graphs. That's kind of not the frozen graph is you've trained it once, it just sits there, it doesn't do anything else, you can't change its state, it's just what it is. A follow-up paper looked at how to do mass editing across GPTs. What's interesting with this is, like, if you can do this successfully, then you can do things like add plasticity to the network, you can do continual learning. And so those are like really interesting things. Now you think about having a transformer which can continually learn. It's like, no, that's wrong. Update its state. And now you're into a very different space. Yeah, you start off hallucinating, but very rapidly you end up kind of tidying up all of those graphs and pruning them back, and you end up with something which is now a much more interesting device. But maybe we can improve those memory units, right? So we're just looking at memory units which are in the middle of the transformer. Just make a different layer. Do something different with it. Do something novel with it. Maybe associative memory. Like, that would be a nice trick. Associative memory, we look at peanuts, we think of monkeys. That's an association, right? Associative memory is very powerful. Associative memory, you can do really fast parallel searches. It's context-based retrieval. You can retrieve from partial data successfully. You can do flexible, efficient data access, which makes it just super high speed. And it's very fault tolerant. It's also, I believe, and maybe Camilla can give me some feedback on this later stage, more robust to adversarial attacks. Which takes you into hot field networks, because the associated memories that you have, hot field networks are the most kind of common ones which you have, and you kind of come across these all the time when you kind of look into the wider field of neural networks. Hot field networks have nodes, everything's connected together, they have weights, they work on this Hebbian learning rule, which is everything that's wired together fires together. They're energy-based models, and so when you hear people talking about energy-based models, like, your mind flips back to these guys, hot field networks. They're one of a class of energy-based models. But classical hot field networks can't store much stuff. They're not very effective. They store about 14% of the node count that they have. That doesn't make it as a successful approach until 2022, when hot field networks is all you need came out, and they showed that actually, if you tweak the way that this is done, these things can scale exponentially with the number of nodes. So the number of data points that you can store is exponential to the number of nodes that you have. This is a huge change. And so this kicked off a whole lot of research and a whole lot of work in the companies, in large tech companies. And for a while, like you kind of only saw energy model stuff being talked about, but it's only within the tech companies. If you look at like the citations outside of that, nothing. It's like it's really quiet, but in the tech companies, you see this stuff going on. The hot field networks have an update function, and they use that for that. A sharply peaked softmax over the energy. So basically, you present it with a pattern, it kind of tries to find the minimum pattern inside itself which matches that, and then it uses a softmax to really hone in on that pattern. So if you have like some stored pattern like this one at the top, and you've got some partial piece of the pattern, then you just give it the partial piece, and it will find like the one pattern and it's the thousands of patterns which kind of looks like that. So you can think of that as a key, and you can think of the thing that returns as a value. Wait a minute, key and a value. Yeah, maybe we should look a bit closer at that. And yeah, sure enough, that's a transformer. So the energy update function, when you make it a softmax in a hot field network, is the same as a transformer layer. And you can so just take the transformer layer, get rid of all the junk, just replace it entirely with a hot field network. So that's what they did. These hot field networks, they store classes of patterns. So you can have patterns like the first one that over here, which is just levels generally. You can have things which focus on a very specific node, or you could have things which are like multimodal, just responding to different things. So when you look through an energy transformer and you look at like what it's responding to, you look at all the nodes and what they're storing, it looks like this. This is the first layer, this is the top layer, and you have kind of general stuff on the bottom. It becomes way more specific in the middle, and it becomes slightly more general at the top. And you have a lot of kind of mapping stuff on the bottom with these kind of levels, which are just balancing things out. Which is kind of like that. So it doesn't matter which way you cut this, whether you kind of build this with a conventional transform or you build it entirely with hot field networks, you end up with this split representation where you're encoding specific elements in the middle and you're encoding structure at the end of the unit. And just as a side issue, one of the problems with so these are called modern hot field networks to differentiate them from the classical ones. They had to make them, one of the reasons they went for softmax was to be able to integrate them into transformers and other kinds of deep neural networks, and so they still run on backbone, which isn't kind of particularly biologically plausible. But there was a good research, I think, thesis, which looked at using a localized softmax at the layer, so that you don't have to do the backbone part. So that becomes interesting. And once again, like when you kind of think that these are more general, these solutions overlap each other in terms of, you think about traditional transformer, and now you're thinking of like energy-based transformers. Mathematically, the models are kind of similar underneath. We're kind of going to expect the same kind of performance, or same sort of same ways of behaving. And sure enough, if you can fine-tune language models with just forward passes too. So you don't need to backpop through it. So if you want to train something, you take a kind of small percentage penalty hit for this. If you want to train something really big, you can just do it with forward passes. So you cut out all of the gradients. So that is a very effective way of going forward. Still a lot to kind of pan out on that, but interesting. So to sum up on that part, transformer layers, you can one-to-one replace them with EPMs. That's an associative memory, does pattern matching, it's got large capacity. You can do that in hardware because they're energy-based models. And that's why I'm interested in them, because I'm interested in making hardware, particularly photonic hardware, because that's a very fast way of building these models. But is this really anything like the brain? Right? We're still kind of with things which are not seeming to be very brain-like. So a nice paper came out from the Cox Science folks. This is Tolman Eckenbaum machine. So Tolman Eckenbaum machine, that's a TEM, unifying space and relational memory for generalization in the hippocampal formation. A lot of words. And that's the paper. But what this is basically doing is it's looking at how spatial knowledge and sensory representation is blended together in the brain. Like how does this get assembled in the brain? When you look at these TEM models, they kind of respond in the same way that the brain responds, because it is a model of the brain. It's not meant for anything else. It's a neuroscience model. And you see that they have grid cells and place cells in them, which respond very similarly to the way that the brain works. So what this is doing is it's taking a structural representation from one part of the brain, and it's taking sensory stimulus from another part of the brain, and it's assembling them together in distinct spatially encoded graphs. Okay? And these are separate for each one. The way they represent that also is that you have patterns in one part of the brain, you have patterns in another part of the brain, and you're kind of merging them together using Hebbian weights in the middle, which, okay, you should know by now that looks an awful lot like an energy-based model, that looks like another hot field network. But when you actually look at the TEM model, it's got some kind of characteristics which make it seem a bit familiar. So once again, you can write it in such a way that you're seeing keys, values, queries across the input, and if you compare that to a transformer, yeah, it's a transformer. This is a great paper which kind of broke this down, and it's kind of important to think about that transformers are doing the same thing. They have when we think back to the transformer model earlier, we were seeing like objects, things in one point, and you're seeing structure in another point, and it's kind of doing that joint representation. And that's what a transformer does, right? So when you know that that's what a transformer does, it's like why the heck are we using it in the way that we're using it to just guess next token? We're just training it completely in the wrong way. So transformers are actually much more brain-like than people think. They're inherently multimodal, because think about it, like that whole spatial representation thing is a multimodal task. They're a spatio-temporal engine, which merges structural and sensory data. Right? So now think about building your data sets to be spatio-temporal data sets. That's a deep one, I'll let that kind of sink in. But yeah, currently we don't train them that way at all. We're just using them all up. So let's change gear. Context. This is a pet hate of mine. When we think about context, like, we go and cover things from the micro scale to the meso scale to the macro scale. Think about the information here. You can look at one of these things. Okay, look at the left-hand side, you're thinking, I don't know, think about the biology of that thing, the biology of the flower. In the middle one, you're thinking about ecosystems, and you can tie the ecosystems back to this. Okay, so you've got a graph of knowledge about this, you've got a graph of knowledge at the meso scale. You can think about how at the macro scale, how the environment kind of impacts the local environment, impacts the micro environment. That's just an enormous graph. Like, obviously, and like, you've kind of taken that in without even thinking about it, right? You processed an enormous diversity of graph-related knowledge without thinking about it. So to do that, you need to be able to break down. Obviously, you can't store like a big graph. We can't have like an enormous graph for everything, because we would run out of space. We need a way of breaking them down. So we must be storing information as some kind of hierarchical set of graphs. And they must be compositional, because if we had to, once again, if you had to store that big graph in a database, it's like you would just be very inefficient, right? But if you can break it down into smaller parts and make it compositional, then it becomes a much more tractable problem to solve. And also, you think about the hippocampus. We're thinking about how it's taking that structural space. So as you look around you in the room, you could stand in any point in the room, and different points in the room that you stand in would fire a different place neuron. But you don't have an infinite amount of space. So when you're encoding something into that space, it's got to be quite small, because you're using the same machinery to encode all your information. And so it has to be able to break down into small chunks which fit in that space so you can encode it. And this kind of takes you nicely into the kind of topological deep learning space, where they're looking at how you break down graphs into subcomponents which can be interrelated. And more specifically, it takes you into things like cyclical Hopf field networks. A cyclical is like a minimal structure that a graph can be broken down into. So there's a lot of work which has been going there, and it keeps coming back into the same space. It keeps coming back into the same Hopf field type energy-based model solution. So now you're armed with the pre-knowledge. You can kind of see where we might be going. So a couple of years ago, this is actually 2022, a year ago, wow, that was quick. Janukun put this one out, it's from Meta. This is on the JEPA architecture, which is joint representations for building world models, basically. The idea behind it is that you have a world model which you build around, and they had the basic kind of component of this is an energy-based model, or a current energy-based model, which builds this joint representation of the incoming information and your world, and it kind of narrows that down to a series of patterns. They looked at this, and this solves a lot of problems in space, but they couldn't build it, and so, or they hadn't been able to build it at the time. But they could see that they had to go down this route for the next generation if you wanted to be able to resolve a lot of the issues which we're seeing with the way things learn. So the next gen architectures that they're looking for, they're more brain-like. They need to be spatio-temporally trained. They're going to be almost certainly EBM based, at least for the next generation. That gives you this associative memory with pattern learning. multimodal, because that whole approach is inherently multimodal. They're going to be pushing for larger context graphs, which are decomposable, because that's the only way that you can collect that information. And the most logical way of doing that is video-based training. And sure enough, right on time, like last week, they got this paper, which is self-supervised learning from images with joint embedding predictive architecture. This is Jet. So this is an energy-based model, supply. It does pattern association. It learns a lot faster. This is a vision transformer, so it's an energy-based vision transformer. It has high-level semantic image representations. It learns them just off bat. It doesn't need handcrafted data augmentations to get it. It just kind of can just jump in and find those itself. And it's converted a lot faster than pixel-based models. So they've just gone for the low-hanging fruit of going for the vision approach. But if you understand what's come before, you can understand why they would have done this and where they're going next. This is forming that kind of hippocampal core to a agent system. And so what you may expect to see is things which move much faster in that direction. But once again, connecting these things up, we still don't know really how to do that yet. But you'll see it happen much faster. So I would say that this is a plausible next step, next evolutionary step in where we're going with the AI architectures which we have. So large context, spatiotemporal, energy-based, associative cognitive architectures. And if you want to know what the implications are for that, then you'll have to come to another talk. So if you'd like to find out more about PMLG, you can grab us at assistedevolution.net, PMLG at assistedevolution.net. We're on Meetup, obviously, because you managed to find us here. Yeah. So on that note, let's open up for some questions for Philippe and for Camillo, and if you'd like, I'll try answering some.